Hello, everyone. In this video, we're going to look at example 2 in section 6.5 on improper integrals. So example 2 says, to the right, you are given the graphs of y equals 1 over x squared. We can see it labeled here. And y equals 1 over x. Calculate the improper integrals of the integral from 1 to infinity of 1 over x squared dx and the integral from 1 to infinity of 1 over x dx. Okay, so let's go ahead and get started. So let's start with this first integral here. So we're going to look at the integral from 1 to infinity of 1 over x squared dx. And so looking at our graph of this function, we see that the lower bound starts at 1, and then the upper bound is infinity. So we know that that means we need to compute the limit as b goes to infinity of the integral from 1 to b of 1 over x squared dx. Okay, so how should we think of that? So b is our upper bound. We could start b here. And that integral computes the area. So as b goes to infinity, we're just going to compute the area under the curve as we go out forever. Okay, and now we're going to do that same thing when we look at the next integral. Start with 1, go to b, but then make b go to infinity. So we're looking at this area under here. So notice the graph of 1 over x squared hugs that x-axis a little closer than the graph of 1 over x. So we're going to see some interesting behavior between these two integrals. All right, let's get back to it though. So we're looking at the integral from 1 to infinity of 1 over x squared dx. Okay, so we rewrite that improper integral using a limit. So now we just need to compute that antiderivative. So 1 over x squared, recall that's just x to the negative 2. So we can just use the power rule to compute that antiderivative. So that becomes the limit as b goes to infinity of negative 1 over x, evaluated from 1 to b. And again, we can see that if you want to see further details here, the antiderivative, we need to add 1 to that exponent and then divide by the new exponent. So that would look like x negative 2 plus 1, and then divide by negative 2 plus 1. So that becomes x to the negative 1 over negative 1, which rearranging terms so we no longer have a negative exponent becomes negative 1 over x. Okay, cool. So I'm just going to erase that to help reduce our clutter here, but feel free to leave it on your paper just for some additional steps. Okay, so now we're going to fill in, we're going to plug in b and 1 in x. So this becomes the limit as b goes to infinity of negative 1 over b minus negative, so it becomes a positive, 1 over 1. All right, so let's think about what happens when we compute the limit. So here, this function, this fraction rather, the denominator goes to infinity. The numerator stays fixed at 1. So again, we have the behavior where 1 is fixed in the numerator, but we're dividing by a larger and larger number. So eventually this entire term just goes to 0. So this is equal to 0 plus 1, which is equal to 1. So in this case, we'd say that this integral converges to 1. So if we added up all the area under this curve, we could just fit it into a box of size 1 by 1. Pretty cool, huh? All right, let's see what happens with the next integral. So now we're going to take a look at the integral from 1 to infinity of 1 over x. So here we have the integral from 1 to infinity of 1 over x dx. So we need to rewrite it as a limit as the upper bound b goes to infinity of 1 to b, 1 over x dx. Right, so the next step here in computing this integral is to compute that antiderivative. So the antiderivative of 1 over x, recall, is that natural log using absolute value. So we just get the limit as b goes to infinity of the absolute value, or of ln, the absolute value of x, evaluated at 1 to b. All right, so let's go ahead and plug in b and 1. So we get the limit as b goes to infinity of the ln of b minus the ln of 1. All right, now let's look at each of these terms. So ln of 1, that's just 0. You can plug it into your calculator. You could think it through. It basically tells us e to what power gives me 1, e to the 0 gives me 1, so that ln of 1 is 0. And then what happens as b gets larger, goes to infinity? So we can look at a natural log function, but the natural log function, or to help us with this integral, and we would see that the natural log blows up as our input blows up. So this term actually goes to infinity. So this becomes infinity. So just reflecting on what we have done, we see that the area under 1 over x, we tried to fit this area into a closed space. We couldn't do it. It would just keep on covering more and more space. Super interesting. And so we call that, we say it diverges. And so maybe a summary, let's just write a summary statement. So therefore, what happens? So we say that the integral from 1 to infinity of 1 over x squared dx converges to 1. And yet the integral from 1 to infinity of 1 over x dx diverges. We don't usually say diverges to infinity. Diverges means does not approach a finite number or goes to infinity. All right, so let's go ahead and close this up with our fact here. So super interesting fact, for any a bigger than 0, the improper integral from a to infinity of 1 over p dx converges if p is bigger than 1 and diverges if p is less than or equal to 1. So this is a super interesting fact. So we can prove this fact by plugging in a different value for that exponent. So by using p and then taking 2 different limits. We're not going to do that in this class. You're welcome to work that out. But this is so amazing. It says that we don't even have to go all the way to 2 in the exponent to get a convergent area down here. We just need to have an exponent that's larger than 1. So 1.000000001 would make that area be finite. Super fascinating, isn't it?